Hello, everyone, and welcome to the Environmental Science and Engineering Podcast channel. Welcome to the channel, and if you're new here, well, if you're looking for in-depth explorations into the world of environmental topics, you know what to do, subscribe.
Absolutely. It's great to be back.
Today, we're diving deep into something really fundamental, but it's often overlooked, and that's the energy dynamics of wastewater treatment plants.
Yeah, it's interesting. This was actually a topic suggested by you, our listeners. And as we started looking into it, it turns out there's a really compelling story to uncover about how much energy these facilities consume, but also the incredible potential for them to actually become energy producers.
Yeah, I think when most people think about wastewater treatment plants, they probably don't immediately think about energy, but these plants are essential for public health and environmental protection, and they require a significant amount of energy to operate.
That's right. We often take for granted the infrastructure that underpins our modern lives, and wastewater treatment is a prime example. The sheer scale of energy involved in keeping these plants running often isn't appreciated, and that's something we really want to shed light on today.
Yeah, so today we're going to examine not only the global and local energy use by these facilities, but also the significant costs associated with that energy.
And then we're going to dive into what I think is the most exciting part, the surprising amount of energy that's actually locked within the wastewater itself and the cutting-edge strategies being developed to make these plants much more sustainable.
Yeah, it's about turning a challenge into an opportunity.
Exactly.
So let's start with the big picture. You mentioned global energy consumption.
Yeah.
What does the data tell us about how much electricity wastewater treatment plants actually use worldwide?
So globally, wastewater treatment plants consume somewhere between 0.1% and 0.4% of all the electricity that we generate.
Okay, so that might not sound like a huge amount at first glance.
It might seem like a small slice of the pie, right? But you have to remember the sheer volume of electricity we use globally. So that fraction, that seemingly small percentage, still represents a massive amount of power dedicated to this essential service.
That makes sense, and I imagine this varies quite a bit depending on the level of development in a given region.
Oh, absolutely. And that's a crucial point in developed nations such as the United States. This percentage jumps significantly to around 3%.
Wow, so that's more than triple the global average.
Yeah, exactly. And this difference really highlights a critical challenge for developing nations as they work to expand their sanitation infrastructure.
Right, because if they don't incorporate energy-efficient designs from the outset, they risk locking themselves into these high energy consumption patterns for decades to come.
Precisely.
So we've looked at the global picture. What about on a more local level? What kind of an energy burden does this place on municipalities?
When we look at the overall energy consumption of a municipality, you really start to see the impact of water and wastewater treatment. These facilities together can account for anywhere from 30 to 40% of a city or town's total energy use.
Wow, that's a significant chunk of their energy budget.
It is, isn't it? Just think about that for a moment. A huge portion of the energy used by your local community is dedicated to ensuring clean water and treating wastewater.
Yeah, it really puts into perspective the importance of finding efficiencies in this sector, doing more with less.
Absolutely.
And that leads us to the financial aspect. We know that energy is a significant operational expense for these plants, but can you give us a sense of just how significant it is?
Sure. So energy costs typically represent about 25 to 30% of a wastewater treatment plant's total operational expenses.
So it's a pretty substantial portion of their budget.
It is. It's actually the second largest expense after maintenance and repair, which takes the biggest slice at around 50%.
Okay, so keeping the physical plant running is the number one cost, but energy is a close second.
Yeah, and it's this constant drain on resources.
And it's not just the ongoing energy bills, right? There's an energy dimension even in the initial construction phase.
Well, that's a crucial point. When you look at the initial capital investment in building a wastewater treatment plant, the electricity and automation systems represent about 10% of the total construction costs.
So while the bulk of the investment goes into the overall construction and the equipment, that 10% still represents a significant upfront commitment to the energy infrastructure needed to run the facility.
Absolutely.
So just to kind of recap what we've discussed so far, we're talking about a sector with substantial energy demands both globally and locally, and where energy costs are a major and ongoing financial consideration.
Right.
So to really get a handle on this, what are the typical rates of energy consumption relative to the amount of wastewater being treated?
So on average, a wastewater treatment plant consumes somewhere between zero point 0.3 and zero point 0.6 kilowatt hours of electricity for every cubic meter of wastewater it processes.
Okay, so we can think of that as the energy intensity of cleaning our water.
Exactly. And the figure often cited as a general average is around 0.45 kilowatt hours per cubic meter.
Okay, and I imagine this can vary depending on the specific treatment technologies being used and the characteristics of the wastewater itself.
Oh, absolutely. The strength of the wastewater, the types of pollutants present, all of those factors can influence the energy required for treatment.
So it's not a one-size-fits-all kind of metric.
No, not at all.
Okay, so we've established that a considerable amount of energy goes into this process, but here's where I think the narrative takes a really interesting turn. Wastewater isn't just something we need to clean up, it's also a surprisingly rich source of untapped energy.
Exactly, and that's what makes this whole topic so fascinating. It's this dual nature. On the one hand, these plants are significant energy consumers, but on the other hand, the very thing they're dealing with, the wastewater itself, holds a significant amount of latent energy just waiting to be harnessed.
So let's dive into that potential for energy recovery.
Let's do it.
Where does this energy primarily reside?
So the energy is primarily stored in two places: the organic matter present in the water and in its thermal content. We can think about it like this. The wastewater is warm, and it's got stuff in it that can be burned.
Okay, so let's start with the organic matter. How do we actually extract usable energy from that?
The primary method for recovering energy from the organic pollutants in wastewater is through a process called anaerobic digestion.
And remind us how that works.
Sure. So, in simple terms, anaerobic digestion is like a controlled composting process. But without oxygen, microorganisms break down the organic matter, and in the process, they release biogas as a natural byproduct.
So it's kind of like how decaying leaves in a forest produce methane.
Exactly.
Okay, and this biogas that's produced, does it have much energy value?
It does. It typically has an energy value of around 6 kilowatt hours per normal cubic meter.
Wow, so that's actually pretty substantial.
And what makes it even more valuable is that we can use this biogas in what are called cogeneration systems or combined heat and power units. These systems can generate both electricity and heat from the biogas.
So you're essentially getting two forms of usable energy from what was originally just waste.
Precisely.
That's incredible. And what about the sludge that's a byproduct of the treatment process? Does that hold any energy potential?
It does. Both the sludge that's produced before it goes through anaerobic digestion and the digested sludge contain a considerable amount of energy.
Okay, so even after you've extracted the biogas from it, there's still energy left in the sludge.
That's right. Undigested sludge has a thermal value somewhere in the range of 20,000 to 28,000 kilojoules per kilogram. And even after digestion, it still has about 12,000 kilojoules per kilogram.
So what can you do with this sludge?
Well, this sludge can be dried and then incinerated in a controlled manner, and the heat released during that combustion process can be captured and used to generate energy.
So it's another way to close the resource loop and extract value from what's often considered a waste stream.
Exactly.
And you also mentioned the thermal content of wastewater itself. It might not be obvious to everyone that even the temperature of the water can be an energy source.
Right, it's not something you might think about right away, but wastewater often maintains a relatively stable flow and temperature throughout the year,
Mhm.
which makes it a very consistent opportunity for thermal energy recovery.
Okay, so how much energy are we talking about here?
Well, even a seemingly small temperature difference can be harnessed. For example,
Hmm.
a difference of just 5 degrees Celsius in 1 cubic meter of wastewater can yield approximately 6 kilowatt hours of thermal energy.
Really? And how is this heat typically utilized?
This recovered heat can be used for a variety of purposes, things like heating buildings nearby industrial processes, or even preheating water for other uses within the treatment plant itself, which further improves its overall efficiency.
So there's a lot of potential there for reducing the plant's reliance on external energy sources.
Absolutely.
So we've got energy in the organic matter, the sludge, and even the temperature of the wastewater. But you also mentioned chemical and hydraulic energy potential. Can you elaborate on that?
Sure, let's break those down. The chemical oxygen demand, or CIT, as it's known in wastewater, is essentially a measure of how much organic pollution is present that can be oxidized.
Okay, can you explain that in a bit more of a layman's terms?
Sure, think of it this way. CIT tells us how much food is available for microorganisms in the wastewater, and the more food there is, the more potential chemical energy is locked within it.
Okay, so higher CD means more potential energy.
Precisely. Now, theoretically, 1 gram of CD has an energy potential ranging from about 17.8 to 28.7 kilojoules, or roughly 0.005 to 0.008 kilowatt hours.
Okay, so if we have, say, 1 cubic meter of wastewater with a CD concentration of 600 milligrams per liter, how much chemical energy are we talking about?
So in that case, the theoretical chemical energy potential is around 2 kilowatt hours.
So that sounds like a significant amount of potential energy just flowing away with our wastewater.
It is, and you're right to point that out, but Here's the catch, the efficiency of our current technologies for actually converting that chemical energy into usable forms like electricity is still a limiting factor.
Okay, so there's a difference between the theoretical potential and what's practically achievable right now.
Exactly. For moderate domestic wastewater with a CI of around 400 milligrams per liter, the theoretical maximum energy we could get is about 1.54 kilowatt hours per cubic meter.
Okay.
However, the practically achievable energy recovery through established processes like cogeneration following anaerobic digestion is closer to 0.20 kilowatt hours per cubic meter.
So we're still a ways off from fully tapping into that chemical energy potential.
We are, but there's a lot of research and development going on in this area, so I'm optimistic that we'll see significant improvements in the efficiency of these energy recovery technologies in the coming years.
Okay, so are there any emerging technologies on the horizon that you're particularly excited about that could help bridge this gap in efficiency?
Oh, that's a great question. And there are a number of really exciting advancements that hold a lot of promise. One area that's particularly interesting is microbial fuel cells. These are devices that can directly convert the chemical energy in wastewater into electricity using microorganisms.
Oh, wow. So that sounds like it has the potential to be much more efficient than the current methods.
It does. And there are also other promising approaches like advanced anaerobic digestion technologies that are being developed to enhance biogas yields and improve the overall energy recovery from that process.
And what about the hydraulic energy we were talking about before? We don't typically think about wastewater systems as having hydroelectric potential.
It's true. It's not as common,
Yeah.
but in certain situations, it can be a viable option in places where there's a significant elevation drop in the wastewater conveyance system or within the treatment plant itself. We can actually harness the hydraulic energy of the wastewater flow to generate small-scale hydroelectric power.
So are there many plants that are actually doing this?
It's not widespread, but it's becoming increasingly popular in areas with suitable topography. The estimated potential energy recovery here is about 0.0008 kilowatt hours per cubic meter for every 10-meter drop in elevation.
Okay, so while it might not be a primary energy source for most plants, it can be a really nice supplemental source in the right conditions. So we're seeing that there are numerous ways to recover energy from the wastewater treatment process itself. But what are some of the primary strategies and technologies being implemented to enhance energy efficiency in the first place? Kind of reducing the amount of energy that we need to put into the system.
Right. So one of the most critical areas for improvement is optimizing the aeration systems. These are the systems that supply oxygen to the biological treatment processes.
And why are those so important?
They're huge energy hogs. Aeration systems can account for a whopping 50 to 60% of a wastewater treatment plant's total energy consumption.
Really? Wow.
So you can see why optimizing these systems is so crucial.
Absolutely.
Hmm.
So how are we doing that? What are some of the ways to make these aeration systems more efficient?
Well, one approach is to implement more efficient diffuser technologies. The diffusers are the devices that actually transfer the oxygen into the water.
Okay.
And there are newer diffuser technologies like fine and micro bubble diffusers that can transfer oxygen much more effectively than traditional diffusers.
So it's about getting more bang for your buck in terms of the oxygen that you're putting in?
Exactly. And another important strategy is using what are called NH-NT-controlled air supply systems.
Okay. And what do those do?
These systems use sensors to constantly monitor the levels of ammonia in the wastewater, which is an indicator of the biological oxygen demand, and they adjust the air supply accordingly.
So you're not just constantly blasting the wastewater with air, you're only providing the air that's actually needed at any given time.
Exactly. It's all about precision and only using what you need.
That makes a lot of sense. And it seems like a relatively simple way to achieve significant energy savings.
It is, and it can make a big difference.
So we've talked about optimizing aeration, but you also mentioned earlier that some of the more advanced treatment technologies can actually increase energy consumption.
That's right. Some of the technologies that allow us to achieve higher levels of treatment, like membrane bioreactors or advanced odor control systems, do come with an increased energy footprint.
So how does energy recovery factor into the equation when we're considering these more advanced technologies?
Well, that's a key point. It's true that these advanced technologies can increase energy consumption potentially by around zero point 0.2 to zero point 0.4 kilowatt hours per cubic meter. But the important thing is that if we can effectively implement energy recovery strategies, we can still aim for net positive energy wastewater treatment plants.
Okay, so explain what you mean by net positive.
So a net positive plant is one where the total energy produced from the wastewater exceeds the total energy consumed by the plant.
Wow, so even with these more energy-intensive treatment technologies in place, they can still produce more energy than they consume.
Exactly, that's the goal.
That's incredible. And what are some of the other technological advancements that are helping to boost energy efficiency in these facilities?
Well, another really significant area is the use of variable frequency drives, often called VFDs.
Okay, I've heard of those, but remind me what they do.
So VFDs are used on large energy-consuming equipment like blowers and pumps, and they allow you to adjust the speed of the motor based on the actual demand.
So instead of running these motors at full speed all the time, you can ramp them up or down as needed.
Exactly. And this can lead to substantial energy savings, especially in systems where flow rates or oxygen demand fluctuate throughout the day.
So it's all about right-sizing the energy input to match the actual needs of the system at any given time.
Precisely.
And you also mentioned some of the more innovative biological treatment processes that can offer energy advantages. Can you talk a bit more about those?
Sure. So one really interesting example is the integration of processes like nitrotation and ammics for the treatment of side streams.
Side streams.
Right. So side streams are these concentrated flows of wastewater that come from certain processes within the plant, like sludge dewatering.
Okay.
And traditionally, we've used a process called nitrification to remove nitrogen from these side streams. But nitrification requires a lot of oxygen, which means it's very energy intensive. But newer processes like the Sharon Anamix process are much more energy efficient.
Yeah.
They require significantly less oxygen, and they don't need an external carbon source to function.
So it's a win-win, less energy consumption and better nitrogen removal.
Exactly.
You know, it's fascinating how all these different technological and biological approaches can be combined to create more energy efficient and sustainable systems.
It really is a very exciting field to be working in right now.
You also highlighted a really compelling real-world example, the Strass wastewater treatment plant in Austria. Can you tell us a bit more about that plan and what makes it so special?
The Strass plant is a great example of what's possible. It's a true success story when it comes to achieving energy positivity.
So they're actually producing more energy than they consume.
That's right. Initially, they were only meeting about 49% of their own energy needs.
Okay.
But through a concerted effort involving both technological upgrades and process optimization, they've now reached an impressive 112% energy self-sufficiency.
Wow, that's a huge turnaround. What were some of the key upgrades that they made?
Well, one major step was implementing that nitrotation and ammics process for treating their digester supernatant that we talked about earlier that really cut down on their oxygen demand. And they also invested in a renewed and more efficient combined heat and power, or CHP system, to maximize energy recovery from their biogas.
Okay, and any other key changes?
Yeah, they also replaced their conventional fine bubble diffusers with a system that allows for intermittent aeration. So basically optimizing the oxygen delivery in their main treatment process.
So it's a combination of both biological and technological improvement.
Exactly, and it's a great example of how these different approaches can work together synergistically.
And this plant serves a fairly substantial population, doesn't it?
It does. It handles the wastewater from a population equivalent of around 90,000 to 200,000 people.
Wow, that's pretty impressive. And what kind of treatment process do they use?
They use a two-stage A-B process.
Okay, I'm not familiar with that. Can you explain how that works?
Sure. So the first stage, the A stage, operates with a very short solids retention time, or SRT, of only about half a day, and a short hydraulic retention time, or HRT, of just 30 minutes.
Okay, and what's the goal of that first stage?
The goal is to quickly absorb as much of the readily biodegradable organic carbon as possible onto the sludge.
So essentially capturing that carbon before it gets broken down too much.
Exactly. And then this carbon-rich sludge is sent to the anaerobic digesters to maximize biogas production.
Okay, that makes sense. And then what about the second stage?
So the second stage, the B stage, has a much longer SRT of around 10 days, and it's focused on achieving high nitrogen removal efficiency. They typically achieve effluent ammonium concentrations of less than 5 milligrams per liter.
Wow, so very low levels of ammonium in the final effluent.
Exactly. And it's interesting to note that only about 47% of the total energy consumption for the entire plant occurs in this B stage.
Really? So that first stage, the A stage, is doing a lot of the heavy lifting in terms of energy recovery.
It is.
This AB process seems to be a central strategy in achieving energy efficiency in wastewater treatment. Can you talk more broadly about how these advanced process strategies like the adsorption biooxidation or AB process contribute to improved energy efficiency?
The AB process is a really compelling alternative to traditional activated sludge systems, especially when the main goal is to maximize energy recovery from the wastewater.
Okay, so how is it different from the traditional approach?
Well, the fundamental principle behind the AB process is to capture that readily biodegradable organic carbon in the wastewater and divert it towards biogas production rather than fully oxidizing it, which is what happens in a traditional activated sludge system.
And why is that beneficial from an energy perspective?
Well, oxidizing that organic carbon through aeration requires a lot of energy, whereas capturing it and sending it to the anaerobic digester allows you to preserve that energy content for biogas production.
Okay, so it's about being strategic with how you manage that carbon in the wastewater.
Exactly, and the two-stage AB process does this very effectively.
Remind us how the two-stage system works.
So in the two-stage AB process, the first stage, the A stage is designed to operate with a very short sludge retention time, often less than a day, and a short hydraulic retention time, typically less than 30 minutes.
Okay.
And these conditions favor the rapid absorption of the organic pollutants onto the microbial biomass without significant breakdown or oxidation.
So it's like a quick grab and go for the carbon.
Exactly, and this results in a primary sludge that's very rich in organic carbon, which makes it an excellent feedstock for anaerobic digestion and biogas production.
Okay, and then the second stage takes care of the rest.
That's right. The second stage, the B stage, operates with a longer sludge age, which allows for the more complete removal of the remaining organic matter and the important nutrients like nitrogen and phosphorus.
So it's a really nice division of labor between the two stages.
It is.
So by essentially front-loading that carbon capture, you're reducing the amount of energy needed for aeration in the initial stage and preserving that energy for biogas production.
Exactly. The high-load A stage is all about minimizing energy consumption while simultaneously maximizing the amount of biogas that can be generated.
That's a great strategy, and this approach seems to be working really well in plants like stress.
It is, and as we discussed before, membrane processes can also be integrated into the B stage of the AB process to further enhance nutrient removal if needed.
So there's a lot of flexibility in how these systems can be designed and tailored to specific needs.
Absolutely.
Well, this has been a really comprehensive and insightful deep dive into the energy dynamics of wastewater treatment. We've covered a lot of ground from the significant energy demands to the incredible energy resources that reside within wastewater itself. And it's clear that there are some really promising strategies and technologies emerging that can make these facilities much more sustainable.
It has been a fascinating discussion, and I think it highlights a really important shift that's happening in the field of wastewater treatment. We're moving away from simply viewing wastewater as a waste product and starting to recognize it as a valuable resource.
A resource for both water and energy.
Exactly. And this is being driven by the growing need for more sustainable and resource-conscious infrastructure around the world.
Absolutely. So let's bring this back to you, our listener. Wastewater treatment is clearly a vital process, but as we've explored today, it doesn't have to be an energy hog.
That's right. The wastewater itself represents a substantial and largely untapped energy resource.
And from the heat it holds to the organic matter that can be converted into biogas, the potential for energy recovery is huge.
The success of the Strass plant in Austria is a powerful real-world illustration that achieving energy-positive wastewater treatment is not just a pipe dream. It's a tangible possibility through smart technology and optimized treatment processes.
And with continued innovation in areas like aeration systems, nutrient removal technologies, and advanced process designs like the AB system, we can make wastewater treatment not only environmentally responsible, but also a contributor to our energy future.
This deep dive raises a really important question as these technologies continue to advance and our understanding of the energy potential within wastewater deepens. How might these developments fundamentally reshape the way we design, build, and operate our water infrastructure in the future?
That's a fantastic point to ponder what new possibilities could emerge as we move towards a more circular and resource-conscious approach to wastewater treatment.
It's an exciting time to be involved in this field, and I'm really looking forward to seeing what the future holds.
Well, thank you so much for sharing your expertise with us today. It's been a really enlightening conversation.
It's been a pleasure.
And to you, our listener, thank you for joining us today on the Environmental Science and Engineering Podcast channel. Don't forget to subscribe to the channel for more in-depth explorations of critical environmental topics. And please leave a comment below when you've had a chance to listen. We're always eager to hear your thoughts and feedback.
And if you have any suggestions for future deep dives, please let us know.
Until next time.
Take care.